I have some material I want to present today. Once I get done with that, then we'll just talk about the questions you have about the take-home quiz, okay? So let me just reiterate what we did last time, right? We talked about vectors in the plane. In other words, two-dimensional vectors, right? And we said if you had A equal to, say, A1, A2, and B equal to B1, B2, then what? Then we defined a number of different things. First of all, we defined the length of A was the square root of A1 squared plus A2 squared, right? And we defined the unit vector in the A direction to be 1 over A times the A vector, right? This is a unit vector in A direction. Now, what do I have to assume about A for that to make sense? What's the length of the zero vector? So like the 0, 0 vector, square root of 0 squared plus 0 squared is the square root of 0 is 0. The length of the zero vector is 0. So we can't do this for the zero vector. But anything but the zero vector, we can calculate the unit vector. Right, and like here's a picture of what's going on. If this is A, right, and maybe A has like length 5, A hat, you could picture it's like this. Right? A hat. A hat. So this is a hat you don't want to wear. Depending on your system of units, like if we were using feet, if you wore this hat, you'd be a foot long, you know. So it could be painful. Now we also defined A plus B, right, which was A1 plus B1, A2 plus B2, right? And we defined a constant times A, a scalar multiple of A, as CA1, CA2, right? And I would remind you, geometrically, we said, like, if this is A and this is B, if we draw them tip to tail, then A plus B is over here, right? Another thing I should mention is, you know, if this is A, then this guy is minus A. Same direction, same length, opposite direction, so diametrically opposed. So that's just a quick summary of what we did last time, all right? So the question that I want to ask today, all right, is how to find angle. How to find the angle between A and B, you know, vectors. So let's call that, let's say, so here's a picture of what I'm trying to do. Here's A, here's B, here's the angle between them, all right? And so if we denote that angle between A and B like this, we could say it's equal to theta in the above picture. So I'm suggesting the angle between A and B is theta. How do we calculate that angle? That's the question I'm asking. All right? That's the question. And if you just look at it and like think about it in terms of trigonometry, it's, you know, it's kind of a challenging question, right? I mean, we could approach it, we could attack it directly, I suppose. But the problem is my picture may or may not make sense because the angle could be greater than 90 degrees, right? So we'd have to think about the like this acute case, but we'd also have to think about the obtuse case. By the way, I said an oblique triangle is one which has an angle which is larger than 90 degrees. That is factually inaccurate. That is untrue. An oblique triangle is just one that does not have a 90-degree angle in it. So I'm grateful for Professor Parker pointing this out to me. She's teaching geometry right now, so she was looking up oblique triangle, and she was like complaining that none of the students knew what it meant, or that. Anyway, so I was like, this means that there's, one of the angles is more than 90. She's like, oh, you don't know what it means either. I was like, no, and I think I may have taught the wrong thing to trigonometry. My bad. So oblique just means not a right triangle. Okay, so I really need to go back and find that video and put a comment on it, but all in good time. Okay, so the solution to this problem is rather surprising, and it requires us to introduce something new, definition. So this is not like the, we could just try to solve this in the acute case through direct trigonometry if we wanted to. Let's see, how would I do that? No, I can't think of it. I really can't think of it in terms of direct geometry. So I'm going to take this indirect approach because it's something we need to learn anyway. So definition, A dot B is A1B1 plus A2B2. I'm sticking with the notation I introduced at the start of this lecture. This is the dot product of A and B. Okay, dot product. So let me give you an example. Example 1, if we had A equal to, let's say, 2, 2, and B equal to 1 minus 1, what's A dot B equal to? So we do the first of the first times the first of the second. So 2 times, 2 times what? Well, it's this formula. This is the definition right here. So we do A1 times B, so 2 times 1 plus 2 times minus 1. It's easier than FOIL. It's just the first with the first, the second with the second, and you add them. So the dot product of 2 vectors is a number. Okay, for one thing, that's a little bit surprising, right? You're taking 2 vectors, you're getting out a number. So that's 2 minus 2, so here's 0. 0. Okay. What does the picture look like here? Let's see. Something like this, right? Here's 2, 2. And 1 minus 1 is something like this guy right here, right? So I think if I did my picture right, you can see that the one lies on the line y equals x, the other one lies on the line y equals minus x. That's a right triangle, right? I mean, there's a right angle between these. See that? That's 90 degrees. So I'm just saying. Okay. Now I'm not explained how the dot product helps us find that angle yet. E2, example 2. Mm-hmm.
Going back to the problem, what's the value of 0? What's the, you probably I was just trying to figure out what the significance of finding that information out was.
Well, it seems like whatever this dot product is, maybe if the dot product of 2 vectors is 0, that's showing us that there's a 90-degree angle between them. We can hope that. I haven't proved that, but that's what you might be tempted to conclude from this example. Another thing we could see, example 2, what happens if we take the dot product of a vector with itself? So like say A is 1, 3, and we take A dot A. Right, so that's 1 times 1, 3 times 3, which gives us 10, which, by the way, is the length of A squared, right? Because A here, the length of A is the square root of 1 squared plus 3 squared, right? Square root of 10. So the dot product of a vector with itself is its length squared. I mean, this is just an example, right? But we can, I think at this point we should stop and, like, what are the properties of the dot product? Notice, yeah, so A dot A is a 1 squared plus A2 squared, right? Which is A squared, right? Or if you like, it's the length of A. Here's the other notation you sometimes see in math, the length of the vector squared. So the dot product of the vector with itself is the square of its length. That's kind of neat. Another thing we might notice is that A dot B, right, is A1 B1 plus A2 B2, right? But that's equal to B1 A1 plus B2 A2, because these are just numbers, right? So yeah, we can commute the numbers, and likewise we can commute the dot product. So A dot B is equal to B dot A. So it's a commutative product. And also, we can look at A dot B plus C and see how that goes. So that's going to be like A1 times B1 plus C1 plus A2 times B2 plus C2, right? Because remember how we defined addition of vectors? B1, B plus C, we just add the first components to get the first component of the sum. We add the second components to get the second component of B plus C. And then multiply this out. You got A1 B1 plus A1 C1 plus A2 B2 plus A2 C2, which is just algebra. And then rearrange the terms. Put the A's and the B's first and the A's and the C's second. What do you got? These two right here give me A dot B, right? And these two right here give me A dot C. So the dot product has this distributive property. It distributes across addition. So this is a pretty neat new operation we're learning here, this dot product. But what does it have to do with angles? Right? What does it have to do with angles? Well, remember the law of cosines? Slightly. We're going to need it to understand. We're going to need it to understand the relation of the dot product to angles. So let me show you. So we're trying to understand if this is A, right, and this is B, right, we'd like to find the angle right here. Okay? So I would point out already that the length of the sides of the triangle that I'm about to construct, here this has length A, this has length B, right? Those line segments, length A and B respectively. So you guys tell me, if I want to put a vector up here that goes like this, from A to B, what do I have to put there? What vector is that? See, so whatever it is, B, whatever, let me call this vector, for lack of imagination, big X. So look at this. A vector plus big X, right, has to be equal to B vector. See that? Because this plus that is equal to that by the tip-to-tail addition. So this forces us to see that the big X vector is actually what? It's actually b minus a. So in other words, vector A plus b minus a gives me b, because the plus a and minus a cancel. All right. Now, let's, for the sake of discussion here, let's, I need to erase this. It's going to be in the way. Let C equal to the length of b minus a. Okay? So then we've got a triangle with opposite side length c to theta and adjacent side lengths a and b. The law of cosines says that c squared is equal to a squared plus b squared minus twice a b cosine theta. So that's the first thing that's true. Let me call this number 1. It's like a court case. What do you call it? The things that oh, exhibit number 1, right? Mm-hmm. Yes, exhibit Roman numeral 1. However, c squared is equal to the length of b minus a squared, right? And what did we learn about the dot product? We learned that the length squared of a vector is the dot product of that vector with itself. So I can do b minus a dotted with b minus a. That's another way to calculate the length squared. But that's wonderful because now we can use the algebraic properties of the dot product to calculate it. And so what we got is b dot b minus b dot a minus a dot b. Minus minus gives me plus a dot a. Oh, there was another property of dot product I failed to share with you guys, but it's easy enough to prove. Like a constant can be pulled inside the dot product or out of it. You can move the constant from outside to inside and vice versa. So essentially I'm doing that with the minus. Anyway, let me not blather on about that. So here we go. Now it's commutative, right? So look at what we got. We've got, what's b dot b? That's the length of vector b squared, right? So in our typical physics engineering notation, that's b squared. Without the vector, just b squared. And since the dot product's commutative, I have minus 2 a dot b from the middle term, right? And finally, a dot a is a squared, right? So this is exhibit 2, okay? Exhibit 2. But these are equal, right? 1 and 2 are equal because they're just two different ways of calculating the length of b minus a. And so what do we have? Let's put them equal. Let's see where it takes us, right? So you've got a squared plus b squared minus 2ab cosine theta is b squared minus 2a dot b plus a squared, right? So just cancel. Cancel the minus 2's. What do we got? We've got ab cosine theta is equal to a dot b. So here's a theorem that we've just proved. A dot B is AB cosine theta. That is a powerful formula because hidden in that formula is the wisdom of the law of cosines. You could say that that formula is the law of cosines. That's not too much of a stretch. And you got to understand that this can be calculated. Excuse me, A1, B1. Should not breathe my tea. That's a bad idea. Like if you have the Cartesian forms of A1, if you have the Cartesian forms of A and B, you can calculate the dot product by just A1, B1 plus A2, B2. This is a simple calculation. And it's a simple calculation to figure out the length of A and the length of B. And if you know the cosine of the angle, you can find the angle, right? So another way to look at this is definition theta is equal to, inverse cosine of A dot B over AB. So this gives us a stone cold formula to define the angle between two vectors. I've never really defined angle up to this point in the course, except in terms of how far you got to go around a circle and the relation between arc length, like basically the definition of radians. This definition here really doesn't have so much to do with that. It's just if you can calculate inverse cosine. Now, that's the rub. Of course, inverse cosine actually involves radians. I mean, but, well, that's not true. There's a way in higher math to define cosine without all that. You can define it in terms of power series and differential equations and such. But anyway, this is a formula for the angle between two vectors. And so like back here, in example 1, does this make sense? If you go back and like look at example 1 in terms of this, well, the angle between them was what? It was 9. I mean, if the dot product of two non-zero vectors is equal to 0, what are you looking at? If you have A dot B equals 0, so it's AB cosine theta, right? If that's equal to 0, and A and B are not equal to 0, it tells you what? It tells you that cosine theta is equal to 0, right? And inverse cosine, we know this. What's the range? 0 to pi, right? Remember that? 0 to pi. And so that means there's only one place where cosine is 0 from 0 to pi. It's cosine looks like this. Or if you like 180, if we're going to go to degrees. Yeah, so this says theta is pi over 2 or 90 degrees, yeah? So I just claimed that on the basis of my really, really clear picture in example 1, but now I've calculated it. It's 90 degrees, for sure. And whenever the dot product of two vectors is 0, you say that those vectors are orthogonal. Orthogonal. It is. Orthogonal. Orthogonal. Which is just a fancy word for perpendicular. So you can also trade it for this symbol. Woohoo. Perpendicular. But the word orthogonal is used sometimes in a more, typically in a more abstract way than perpendicular. People will talk about perpendicular. They're probably talking about 2 or 3-dimensional coordinate geometry. The word orthogonal applies to other things like music. It does. So music, you can look at what's called the Fourier Decomposition, which is essentially a decomposition of the book, of the music into notes, into sums of harmonics. And harmonics of different frequencies are orthogonal with respect to some sort of generalized dot product. What's that? Oh, good. So, for vectors in the plane, there are two orthogonal directions we typically work with. So let me talk a little bit about that. Here, this is x and this is y, right? So in typical physics books, they do something like this is I, the bold-faced I, and this is a bold-faced J. So like I is 1, 0, J is 0, 1. So if you take this one dot with that one, you get, which is what? 1 times 0 plus 0 times 1, also known as 0. So in other words, I hat is perpendicular to j hat, right? These are perpendicular vectors. Now, I personally, in physics, this notation is not always used. Sometimes in physics, you'll see a better notation used, in my opinion, better, which is x hat and y hat. So these are unit vectors in the direction of increasing x, unit vectors in the direction of increasing y. If you're interested, you can also look for like r theta coordinate system. R hat looks like this. So r hat would be vectors in the direction of increasing r. So it's not constant, right? Like x hat is the same no matter where you are on the xy plane. If you ask, hey, what direction is x increasing? And a length 1 vector in the direction in which x is increasing, the answer is always that away. It's just that way, right? If you're in the xy plane and you ask, okay, I'm at a point in the xy plane, which direction is the radius increasing? That depends on where you are, right? These are different vectors at different places. And you could also likewise ask about what's theta hat. Theta hat is perpendicular to r hat. It's like so. Hey, come on. So these guys are theta hat. So like r hat dot theta hat is likewise equal to 0. That speaks to the fact that the polar coordinate system is what's called a, curses. I want to say orthogonal coordinate system. There's another word I'm not thinking of at the moment, but the polar. So like the thing is, if you look at the lines which describe constant radius in polar coordinates like this, right? Those are constant radius, right? What are the constant angle lines in the polar coordinate system? They're rays, right? And if I drew my picture right, any of these rays, if you look at places where they intersect, right? They intersect such that the tangent, what are called the tangent lines to those curves, are perpendicular. I know you guys don't have a definition of tangent lines yet because you're not in calculus, right? But soon enough you'll be there. It's not that complicated. What's that? You don't want to be there? But do you need to be there? In many ways, calculus is easier than this class. You don't want to do it. So let me do one example of this dot product business here, and let's see here. I guess I should mention, if you have A, you've got A1, A2, right? You could write that as A1 times 1, 0 plus A2 times 0, 1. So this is A1 I hat plus A2 j hat. So like A1 I hat is the vector component of A in x direction. And likewise, A2j is vector component of A in y direction. So I mentioned before that the numbers are the scalar components. These are the vector components. And just to, try to finish the story here, if this is A, right, then here's the vector component in the x direction, A1I hat. And here's the other one, A2j hat. And so a vector is literally the sum of its vector components. I couldn't say the same for scalar components because when you add numbers together, you don't get a vector. These are objects of different type, right? So one of the quickest ways for me to tell a Calculus 3 student just does not care about my course is when they write things like vector equals to number. It's like, hey, I don't care about your course. It's also true in physics. Like when I taught physics, I see students that are just like wholesale confusing vectors and numbers. Like, ooh, that is a student who has not studied much. But anyway. So actually, I will forego the example of actually using this to find the angle between vectors. We'll do that next time. I want to save the rest of the time to answer your questions about whatever questions you have about the quiz. So unfortunately, I don't have a copy of it with me, but I'll open it up. If you give me a second here, I'll get it out. So while I'm doing that, you guys think about what's most important to ask about. Everything. So you just want me to work the whole quiz in the next 15 minutes?
If physically possible, then yes.
If you could just pull out the answer sheet, put them up there, and tell us kind of sort of how you got there.
Let's see
Just
here.
have like a foundation to build off of for the information and how to work it. Because it's annoying because I know I've written down the information from the actual class.
Mm-hmm.
It's just clearly I haven't retained it. And I've missed the important snippets of the actual formulas and stuff. So I'm like,
But,
well, it's just I don't have the
something I should say is when you're working on it, you get stuck, you don't know what to do, just email me. I'm stuck on this problem. Could you give me a hint? I am perfectly happy to answer those kind of emails. Let's see here. So find polar coordinates for the point -3, 5. How would you do that?
I just took a shot in the dark, and I was like, okay, I'm going to go off the first situation that we did
Uh-huh.
with -3 squared plus 5 squared
So r
equals r.
square root of -3 squared plus 5 squared. Okay, great.
Gave us
That gives you r.
36
Mm-hmm.
to square root of 36r.
Well, r should be a number. 20.
Oh.
I think it should be square root of 34 for what it's worth. Oh, you're saying that's 6.4?
Oh, I already messed up. Great.
So that's, yeah, the radius should just be a number. How do you find the angle here?
Oh, I have to get that variable. Because what were we on, dude?
I just know that we were on the wrong stuff now.
Oh, we weren't even in the same category,
Hmm.
I don't think.
And so you need, your polar coordinates, right? So r and theta. What's theta?
Oh, that's where we take the inverse of tangent.
Okay, so if you take the inverse of tangent of, 5 over -3, what do you get?
-60 basically.
negative 60, basically? 60.59?
Oh, no, not 60.59.
I think you're using radians. So like this is the first thing we have to settle, because to do the later problems, basically finding the polar form of the number is, or the complex number later, that's really one of the fundamental things that gets you started on the other calculations. So minus 59.04. Now, is that right, though? I mean, where would that be? That's not where we're supposed to be, is it? Mm-hmm. So theta is equal to what? How about we just, if we add 180 degrees to that, that should get us the right thing, right? Because, so 180 degrees minus 59.04 degrees. Basically, we're saying go to 180 and go back that much. Yeah. So 120.96. So there you go. That's the answer to problem 1. Don't tell the others. Ha ha ha. I'll be like Monday, so did you guys watch Friday's video? I'm like, no, I didn't get around to it yet. I was like, oh, that's too bad. So that's problem 1. So you've got, for the 0.44, actually, I think we should skip problem 2 and go on to problem 3. I'll let you guys look at problem 2. It's a little bit tricky, but you'll figure it out. So my advice for problem 2 is to start by doing exactly the same thing we did for problem 1, but then pay attention to the instructions. You have to have r less than 0, right? So we learned that once you have a given point, if you want to make the radius negative, you have to add 180 degrees to the angle and keep the radius the same. So, oh, I've already said too much. 4 minus 4. Problem 2. I didn't help, so I'll just, was it 4 minus 4? All right, where is that? Right. So this is equal x and y, that's 45 degrees, right? So 45 degrees in the clockwise sense. What's r for this? So, yeah, square root of 32. So we could say that the polar coordinates to this are r equals the square root of 32 and minus 45 degrees, right? I'll write it out. So I'm going to call it r prime. R prime equals square root of 32. Theta equals to minus 45 degrees, right? Theta prime. But what are we asked? We're asked to let r less than 0 is requested in the problem statement. So how do I find polar coordinates that have r? So I could say r equals to minus the square root of 32, and then the theta over here. So I have to add 180. What's 180 plus 180 less 45 is what? 140 minus 5, 135. So that would be the answer to problem 2. So you gotta, if you have r negative, you have to take the right angle, the correct polar angle, and add 180 to it. So this is that silly, if we use negative radius, it flips it over the pole, right? And we saw that that was important to the to the study of graphing, right? So next, we're given z equals to 3 root 2 what are we given? Problem 3. Z is equal to 3 times the square root of 2 times e to the pi I over 4, right? And nope, w equals to 2i. And then the question is, find polar, we'll find the Cartesian and polar form of ZW. So ZW is 3 root 2 e to the pi I over 4. Yep. Mm-hmm.
Does the 2i factor into the square root of 2?
No, I mean, well, let me put it this way. So the way to do this is we've got 6 root 2. The 2 just goes to that. 3 times 2 is 6, you know? I, on the other hand, if we write that in a yeah, we need to write I as an exponential. So that is e to the pi I over 2. We saw that in class before. E to the pi I over 2 is equal to I. I'll remind you why. E to the pi I over 2 is cosine pi over 2.
So I actually did something similar in mine.
So that's just I. Now we can add these. We get 6 square root of 2. E to the, this plus that is 3 pi I over 4. Right? Because a half plus a quarter is 3/4. So this shows that, you know, r is equal to 6 root 2, and theta is 3 pi over 4 for ZW. Those are the polar, that's the polar coordinates for ZW. So this is the thing, if we have the number written in imaginary exponential notation, then you can read the polar coordinates directly from it. Oh, sorry.
You're fine, just mirror side.
So these are the polar coordinates for ZW, all right? How do I find the Cartesian coordinates? I just work it out. So like ZW is 6 root 2, and then I do, what is this in terms, like how do we convert from imaginary exponential back to Cartesians? Well, we use the fundamental relation that is cosine of 3 pi over 4 plus I times the sine of 3 pi over 4. And what are those values? You could get out your calculator, right? Or you could be lazy like me and use graphs. Right. So the cosine is negative root 2 over 2, right? Well, negative 1 over root 2, right? I could write it that way. And then plus I, 1 over root 2. Positive sign, negative cosine there. Because after all, 3 pi over 4 is in quadrant 2, where cosine's negative and sine is positive, right? Not surprising. The root 2's cancel, and we get minus 6 plus 6i. That, my friends, is the Cartesian form of ZW, A plus BI format. So that's problem 3.
That makes a lot more sense than what I was trying to do. I can't tell you what I was trying to do. At that point, it was me and him looking at each other like, what do we do here? And then, well, maybe it's this one. Thanks a lot.
We try to pull information from the actual, like, notes that we've taken throughout class.
Uh-huh.
Put pieces together.
So for problem 4, you've got z is 1 minus I root 3.
And then we just do plus the power. So basically, 9 minus the square root of 3.
Now that is the temptation. So you're supposed to, again, find the Cartesian and polar forms of this, right? Find Cartesian and polar form. I'll get it. So yeah, if you could. I forgot you're sitting right there. Z to the 5th. So the one thing you must not do is actually just multiply it out 5 times. That would be the worst thing. Do not do that.
I thought about that. I really did. And I was like, it can't be that simple.
So you find, well, you can't, I mean, you could do that, but that would be a pain. So what you want to do is find r and theta such that z is r e to the I theta. Step number 1, you find the radius and the standard angle for this thing. Find the polar form of the number and write it using the imaginary exponential. So, of course, r is square root of 1 plus square root of 3 squared, right? Also known as the square root of 4, also known as 2, right? And the angle here, I think, is just inverse tangent of minus root 3 over 1. I think that makes sense because here you're down here. So inverse tangent works. And I do believe that is minus pi over 3. You should check me on that, but I think it's minus 60 degrees. I wouldn't trust me. I would check it in the calculator. So once you have that, what's z to the 5th? See, taking the polar form of the complex number and raising it to the 5th power is easy. You just do 2 to the 5th, and then e to the minus pi I over 3 to the 5th, which is just multiplied by 5. It's minus 60, though, right? Yeah. And so what do we get? We get 32 exponential, I'll write it this way, exponential of minus 5 pi I over 3. So what are the polar coordinates of z to the 5th? There r equals 32, and theta equals minus 5 pi over 3, right? I should say, let me call it, I've used r for something else up there, so let me call it r prime. R prime equals 32, and theta prime equals minus 5 pi over 3 for z to the 5th, right? How do you find the Cartesian coordinates of z to the 5th? Same way we did in the last one. You just, what do? This is what? This is 32 times what? Times the cosine of 5 minus 5 pi over 3 plus I times the sine of minus 5 pi over 3. So whatever that is, that will give you the real part and the imaginary part explicitly, just like in the last one.
So positive, it's going to be positive 2 squared, oh, yeah, 2 squared over 2, and then negative 2 squared over 2.
Yeah, I don't know right offhand. 5 pi over 3.
Oh, it's 3, not 4.
Yeah, 5 pi.
And then negative 3 squared.
And it's negative 5 pi over 3, so I got to be careful. I mean, you could add 2 pi to that. That wouldn't change the answers, right? So, I believe, I mean, you guys check your calculators, but I think that's 32 times 1/2 plus I root 3 over 2. I could be wrong, though.
I feel like sine
Well, my logic was, since cosine and sine are 2 pi periodic, I can add 6 pi over 3. 6 pi over 3 is 2 pi. So this should be the same as cosine pi over 3. And this should be the same as like sine of pi over 3. And I happen to know cosine of pi over 3 is 1/2, and sine of pi over 3 is root 3 over 2. So to picture it, minus 5 pi over 3 would be like this. But geometrically, that's coterminal with pi over 3. But so, and then of course, so like 16, right? 16 plus I times 16 root 3. That's the Cartesian form of z to the 5th. Does that make sense? So that's number 4. I know we're out of time. Do you guys have a minute? I can keep going if you guys have time, but if you don't. All right, well, let's keep going then. Problem 5. What is problem? Yeah, well, I mean, this is the point of the take-home quiz, is to hopefully get you guys to understand. So, problem 5. What is problem 5? We're supposed to calculate the third root of 2 minus 2i. And what else are we supposed to calculate? Okay, so, and I did not force us to put it in Cartesian form or anything, right? So any form of the answer will do. Okay, so here's the deal. If z is r e to the I theta, right? Then the third root of z, by definition, is the third root of r in the real sense times e to the I theta over 3. That's all you got to do. So to solve this problem, we need to first find the polar form of the given number. Once we do that, we just have to take the third root of the radius and divide the angle by 3. That's it for the first thing. So if we've got z is 2 minus 2i, right? Let's picture that. That is down here, isn't it? So what's the angle? What's this angle here? Like the x and the y are equal, right? It's a 45-degree angle. So it's you know, and what's the radius? What's the length of z? Magnitude of z, or r, square root of 2 squared plus 2 squared, right? Square root of 8. So we've got square root of 8 e to the minus I pi over 4. That's the polar form of the complex number. That's the starting point for the calculation. Figure out the polar form. And so now we can do it. So the cube root of z is the cube root of the square root of 8, all right? E to the I minus I pi over 4 divided by 3. I'll clean that up a little bit. That is the 6th root of 8, e to the minus I pi over 12. You guys know that that's how roots work? Do you want me to explain why? So cube root of 8, cube root of the square root of 8 is 8 to the 1/2 to the 1/3 power. So when we have that kind of, pattern with our exponentials, we multiply the exponents. Well, that's the 6th root of 8. Whatever it is, anyway, it's a number. So so there you go. That's the principal third root. Oh, it's okay. Oh, there's a class in here afterwards, isn't there? I better bail. And then so this one, it is the third root, and then zeta 3 times the third root, and then zeta 3 squared times the third root, where the third root z is e to the 2 pi I over 3. If you look back in your notes, we did that. Anyway, I guess I got to shut this down. Sorry, guys. I forget that we share this building with other people. They're not. Yeah, well. Yeah, sure. Why not? All right, let me get out of here before I. But most of the, I think I haven't, I'm finding the polar form of the number in the question.